Antarctica is often imagined as a simple, white desert at the edge of the map. But beneath that icy surface lies a complex continent. Buried mountains, lakes sealed for millions of years, glaciers capable of raising sea levels, and ecosystems that survive at the very limits of what is possible. This journey explores both the visible and invisible Antarctica, from its extreme geography and the history of its exploration, to the secrets hidden within its ice abysses, the life that depends on them, and the scientific, political and human decisions that will define the future of Earth's most mysterious continent. Viewed from space, Antarctica appears as a simple white disk at the far south of the planet. But that icy circle is an entire continent, covering more than 14 million square kilometers, almost 1.5 times the size of the United States. It's not just ice floating in the ocean. Beneath most of that surface lie mountains, plateaus, and deep basins, covered by an ice sheet that in some places exceeds 4 kilometers in thickness. The continent isn't centered exactly on the South Pole, but rather shifted towards the Eastern Hemisphere. This is why we speak of two major geographical units, East Antarctica and West Antarctica. The former is much larger, higher, and more stable. Its ice rests on an ancient, elevated continental block. The latter is smaller, fragmented, and largely supported by bedrock below sea level, making it much more vulnerable to ocean warming. Between the two regions lie, or are, almost semi-enclosed seas, such as the Ross and Weddell Seas, where enormous floating ice platforms. The Ross and Filchner-Ronne platforms act as docks that contain the flow of glaciers towards the sea. On this rocky base rests the largest mass of ice on the planet. The Antarctic ice sheet holds approximately 90% of Earth's ice and nearly 70% of the world's fresh water. If it were to melt completely, global sea levels would rise by several tens of meters, reshaping all the planet's coastlines. But for that to happen, profound and prolonged climate changes would be necessary. For now, this ice acts as a gigantic climate memory, accumulated layer upon layer over hundreds of thousands of years. The climate of Antarctica is extreme even by polar standards. It is the coldest, windiest, and driest continent on Earth. On the coast, during the austral summer, temperatures can reach a few degrees above freezing and even exceed 10 degrees Celsius in some very localized areas. In winter, however, they easily drop below -40 degrees Celsius. In the high interior on the eastern plateau, conditions are even more severe. Summer temperatures rarely rise above -30 degrees Celsius, and winter temperatures have been recorded below -80 degrees Celsius. The absolute record was registered at the Russian Vostok station, with -89.2 degrees Celsius, the lowest air temperature ever recorded on the planet's surface. Despite its image as a snowy world, Antarctica is technically a desert. Average annual precipitation, measured in water equivalent, is around 150 millimeters, less than in many hot deserts. The difference is that almost all of that moisture falls as snow and, due to the extreme cold, it practically never melts. Over time, the snowflakes compact, transform into ice, and begin to flow slowly toward the coast, feeding gigantic glaciers. Where they reach the ocean, they form ice shelves that can be hundreds of meters thick and extend thousands of square kilometers out to sea. Another fundamental characteristic of the continent is light. Due to its extreme latitude, Antarctica is subject to an annual cycle of light and darkness very different from the rest of the world. Near the South Pole, the sun remains above the horizon for months in summer and disappears completely during winter. That means days of continuous light, with the sun rotating in low circles above the horizon, followed by a polar night of several weeks or months in which only the moon, the stars, and sometimes the aurora australis break the darkness. This alternation affects the climate, the behavior of the winds, and human logistics itself. In many scientific bases, heavy operations are concentrated in the summer, while the winter is dedicated to long observations and basic survival. Human interaction with this continent was a late development. For centuries, the idea of a vast terra australis was more of a geographical hypothesis than a proven reality. Mariners like James Cook approached the edge of the ice in the 18th century and crossed the Antarctic Circle for the first time, but the conditions of the sea, ice and climate prevented them from reaching land. It was only at the end of the 19th and beginning of the 20th centuries that the phase known as the heroic age of Antarctic exploration began. Between the 1890s and the First World War, a series of expeditions from different countries ventured into the continent with both scientific and geographical objectives. They mapped sections of coastline, established camps in places like the Ross Sea, and made the first journeys inland. In 1911, Roald Amundsen's expedition reached the geographic South Pole for the first time, after advancing from the Bay of Whales using dog sleds. Just weeks later, Robert Falcon Scott's British expedition reached the same spot by a different route, but his team perished on the return journey. Around the same time, Ernest Shackleton failed in his attempt to cross the continent coast to coast when his ship, the Endurance, became trapped in the ice of the Weddell Sea. However, his leadership in the retreat and rescue of the crew became one of the most famous survival stories of polar exploration. After that period, Antarctica entered a different phase. Airplanes, modern icebreakers, and radio communications transformed how the continent was explored. At the same time, the geopolitical rivalries of the 20th century began to extend onto the ice. Several countries made overlapping territorial claims, and the possibility of using the continent for military purposes or resource exploitation became a cause for concern. In this context, science played an unexpected role as a point of convergence. The International Geophysical Year of 1957 to 1958 marked a turning point. 12 countries established permanent bases and organized a coordinated campaign to observe the climate, Earth's magnetism, the ionosphere, glaciology, and seismology. From this effort emerged the idea of an international agreement that would guarantee that Antarctica would be reserved for peaceful and scientific purposes. The result was the Antarctic Treaty, signed in Washington in 1959 and in force since 1961. The Antarctic Treaty establishes some basic principles. The continent can only be used for peaceful purposes. The installation of military bases and the carrying out of nuclear tests are prohibited. The disposal of radioactive waste is banned, and the possibility of making new territorial claims is suspended for the duration of the agreement. Furthermore, it guarantees freedom of scientific research and the exchange of information and personnel between countries. Over time, the system expanded with specific protocols, including the 1991 Madrid Protocol, which declared Antarctica a natural reserve dedicated to peace and science and explicitly prohibited mining. Today, more than 50 countries are part of this legal framework, which has kept an entire continent free from armed conflicts and direct industrial exploitation. Under this legal framework, Antarctica has become a unique natural laboratory. Ice cores are extracted from its ice, allowing scientists to reconstruct the planet's climate hundreds of thousands of years ago, layer by layer, by analyzing trapped air bubbles and dust particles that tell stories of volcanic eruptions and changes in greenhouse gas concentrations. the effects of stratospheric ozone depletion were first clearly observed in its atmosphere. Astronomical observatories and particle detectors, such as those for neutrinos, are located there, taking advantage of the extremely clean air and near-total winter darkness. At the same time, the continent serves as an early indicator of global changes. Sea ice extent, the mass balance of the large ice sheets, and the temperature of the Southern Ocean are parameters that are constantly monitored to detect warming trends, ice loss, and changes in currents. In recent decades, worrying variations in sea ice extent and stability, in some regions, especially in West Antarctica, have been recorded, placing the continent at the centre of the debate on climate change and the future of sea level. However, everything visible from the air, those immense white plains, the ice shelves, the mountains barely visible, is only the surface. Beneath kilometres of ice lies an unknown geography. Entire mountain ranges buried underground, canyons deeper than any exposed on the planet's surface, deep basins filled with ancient ice, and networks of subglacial lakes and rivers that have never seen the light of day. To descend into the invisible Antarctic, you don't need a tunnel, but waves. The ice, opaque to our eyes, becomes transparent to certain radio frequencies, seismic vibrations, and subtle variations in the gravitational field. For decades, scientific teams have flown over the continent with aircraft-mounted radar antennas, detonated small seismic charges on the surface, and dragged instruments across the ice to detect minute changes in gravity. Each of these methods contributes a piece of the puzzle: the thickness of the ice, the shape of the bedrock, the presence of liquid water trapped deep underground. The result of this effort is a map that contradicts the satellite's initial impression. Where the eye sees a uniform white plain, geophysics reveals a rugged landscape, full of valleys, ridges, and gigantic basins. One of the most surprising discoveries was the existence of an entire mountain range, comparable in size to the European Alps, completely buried under the ice of East Antarctica, the Gamburtsev subglacial mountains. These mountains are located roughly in the center of East Antarctica, under more than 600 to 800 meters of ice in some areas and more than 2,000 meters in others. Ice-penetrating radar data revealed profiles that left no room for doubt. Sharp peaks, deep valleys, a relief typical of an alpine landscape carved by ancient glaciers in the distant past. What is extraordinary is that this landscape was subsequently buried and protected by the formation of the vast Antarctic ice sheet. Instead of being eroded over millions of years, the Gamburtsev Mountains were frozen in time, as if an ice mold had preserved an ancient version of the Earth's surface. The existence of this mountain range has direct implications for the history of the continent. It is believed to have acted as a nucleation nucleus for the formation of the East Antarctic ice sheet. By rising above the surrounding environment, it cooled the air, favoured snow accumulation, and allowed the first glaciers to stabilize. When the global climate changed and the ice expanded, that core became the heart of one of the largest ice structures on the planet. Understanding how and when that process occurred helps reconstruct Earth's transition to a climate dominated by permanent ice sheets. The Gamburtsev glaciers are not the only hidden system. Farther west, the Ellsworth subglacial high and other buried regions reveal mountain ranges, plateaus, and basins that channel the flow of ice. The shape of the bedrock beneath Antarctica determines where glaciers advance, where compression zones build up and thicken the ice, and where deep basins open up that can fill with water. This combination of rock, pressure, and internal heat gives rise to another of the continent's most intriguing phenomena: subglacial lakes. Contrary to what one might think, not everything beneath the ice is completely frozen. At great depths, the pressure exerted by kilometers of ice lowers the melting point slightly, and the geothermal heat emanating from the Earth's interior provides enough energy to keep small amounts of water in a liquid state. When conditions are right, this water collects in depressions in the bedrock, forming lakes that can reach tens or hundreds of kilometers in length. The ice covering them acts like a rigid roof, isolating them from the outside atmosphere for hundreds of thousands or even millions of years. The most famous example is Lake Vostok, hidden beneath the Russian research station of the same name in East Antarctica. Radar and gravimetric data revealed that it is a body of water approximately 250 kilometers long and up to 80 kilometers wide, with an estimated average depth of several hundred meters. It is enclosed under nearly 4,000 meters of ice. Its liquid surface has not been in direct contact with the atmosphere since long before the appearance of Homo sapiens. It is estimated that the lake's water is renewed very slowly through a cycle in which the ice at the base melts and refreezes in other areas, carrying nutrients and sediments with it. The possibility that such an ancient and isolated lake could harbour life forms adapted to extreme conditions spurred several international projects to study it. However, drilling into this environment without contaminating it with microbes and substances from the surface presented considerable technical and ethical challenges. Drilling progressed for years, using special fluids to prevent the well from closing due to ice pressure. When the lake's roof was finally reached, contact was brief and controlled. Samples recovered from remelted ice in the contact zone suggested the presence of microbial DNA, although the debate over what portion is due to external contamination and what portion to indigenous life is still ongoing. Lakes like Vostok and others, such as Lake Ellsworth or Lake Whillans, are of interest not only to biologists. For astrobiology, they represent a natural analogue to the oceans hidden beneath the ice of worlds like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn. On those bodies, a global ocean lies beneath a thick layer of ice, fueled by possible internal energy sources. Studying how life can survive in a dark lake under the Antarctic ice helps in designing missions and strategies to detect life in those extraterrestrial oceans. Antarctica also harbours networks of moving water. These are not just isolated lakes, but systems connected by subglacial channels and rivers. Radar images and changes in ice surface height have shown that some lakes fill and empty over time, as if opening and closing invisible valves. When they empty, the water flows beneath the ice, lubricating the base of glaciers and altering their rate of advance. This hidden plumbing directly influences the stability of the ice sheet, because areas with more basal water can slide faster towards the sea. At the same time, subglacial basins can reach extreme depths. Beneath some glaciers, canyons have been detected whose bottoms lie thousands of meters below sea level, much deeper than the ocean trench measured from the surface of the bed to sea level. These valleys, carved by ancient knowledge geological processes and then filled with ice, are potential weak points. If the ocean reaches them, water can seep beneath the ice and trigger accelerated retreat. This entire hidden world puts the idea of Antarctica as a simple ice sheet into perspective. In reality, there is a complex system in which buried topography, geothermal heat, liquid water, and ice flow interact on timescales ranging from days to millions of years. Each new radar map reveals additional details: a valley deeper than previously thought, a previously unknown lake, an area with more internal heat that could accelerate basal slippage. Understanding this subsurface is not merely a geographical curiosity. it largely determines how the Antarctic ice sheet will respond to global warming. A glacier resting on high cold rock behaves one way. Another situated in a deep basin, below sea level and with liquid water at its base, responds very differently when the surrounding ocean warms by a few degrees. Subglacial valleys and canyons then become potential corridors through which warm water can advance inland, undermining the ice from below. On the map of the invisible Antarctic, some of these corridors converge in key areas, veritable points of support containing enormous volumes of ice. There, the presence of deep basins beneath seemingly stable glaciers has sparked growing concern. If the ocean reaches these points and the slippage accelerates, the lost ice could translate over centuries into meters of sea level rise. It is in these icy abysses where the rock plunges thousands of meters below sea level, and the ice rests on a bed sloping inwards, where the future of many of the world's coasts begins to be defined. Antarctica is not just a frozen continent, it is a moving ice system. Although the landscape may appear static, almost the entire interior of the continent is made up of a vast ice sheet that slowly flows toward the coast, channeled by glaciers. These rivers of ice, some the size of countries, are responsible for draining the mass accumulated inland into the ocean. When they stabilize, global sea levels barely change. When they become unstable, the entire planet feels the impact. A typical Antarctic glacier functions like a conveyor belt. The snow that falls inland compacts and, over time, flows downhill. Where the ice ceases to be supported by the bedrock and begins to float on the sea, lies the so-called grounding line, an invisible but crucial boundary. If this line retreats further out to sea, the glacier loses friction, accelerates, and exports more ice to the ocean. If it remains anchored to a stable topography, the system can remain in equilibrium for thousands of years. Antarctica hides a complex topography beneath its ice, with deep basins and subglacial canyons that, in some cases, make this equilibrium extremely fragile. The most extreme example of this fragility is the Denman Glacier in East Antarctica. From the surface, Denman is just a tongue of ice extending into the Mawson Sea. But beneath this apparent simplicity lies the deepest point on Earth not covered by oceans, a canyon plunging more than 3,500 meters below sea level. This depression, carved by tectonic and glacial processes dating back millions of years, acts as a vast channel through which ice can slide inland. Satellite studies over the past few decades have shown that Denman's grounding line has retreated several kilometers in just over 20 years. The main cause is the influx of relatively warm ocean water beneath the glacier's floating tongue, which thins the ice from below. As the base loses thickness, the grounding line moves inland, entering an area where the bedrock slopes toward the continent rather than the sea. That geometry, technically called a retrograde bed, is the key ingredient in a process known as marine ice sheet instability. The logic is simple and worrying. When a glacier, supported below sea level, retreats to increasingly deeper ground, the thickness of the ice at its grounding line increases, and therefore so does the flow into the ocean. This increased flow further thins the ice, favouring a new retreat of the grounding line. The result is a positive feedback loop. Each step back facilitates the next. In the case of Denman, models indicate that if the entire basin, drained by this glacier, were to empty, global sea levels could rise by about 1.5 meters. This wouldn't happen in decades, but over centuries, and once the process is set in motion, it would be extremely difficult to stop. For a long time, East Antarctica was considered relatively stable, in contrast to West Antarctica, which was considered more vulnerable. Denman and other glaciers in that region have forced a reassessment of this perception. Their recent behaviour suggests that even the cold and safe areas of the continent can respond rapidly to the presence of warm water at depth. This water comes from ocean currents that, as they warm and change course, begin to seep beneath ice shelves that were previously better protected. The hidden Antarctic in this case is not just buried mountains, but channels through which the ocean silently invades the base of the continent. On the other side, in West Antarctica, the ultimate symbol of this threat is the Thwaites Glacier, nicknamed the Doomsday Glacier. Its extent is comparable to that of a country like the United Kingdom, with ice more than 2 kilometers thick in some areas. Thwaites flows into the Amundsen Sea and acts as a kind of plug, supporting a significant portion of the West Antarctic ice sheet. If this plug fails, not only will the Thwaites ice be lost, but neighbouring glaciers that currently rely on its outward advance will also be destabilised. In recent decades, satellite observations have recorded accelerated thinning, the appearance of crevasses, and the retreat of Thwaites' grounding line onto a bed that, like Denman Glacier, is sinking inland. The floating ice shelf that holds it in place is being eroded from below by relatively warm waters from the depths of the Southern Ocean. In some areas, cavities hundreds of meters high have been detected under the ice, veritable empty cathedrals where water circulates, melts, and sculpts the glacier from within. Recent models explore various warming and climate variability scenarios. Some show that even without significant additional temperature increases, the combination of a retreating ice bed, intrusive ocean water, and increasingly fractured ice could lead to the collapse of Thwaites within a few centuries. Its direct contribution to sea level rise is estimated at several tens of centimetres, but the most worrying effect would be the destabilisation of the entire West Antarctic ice sheet, with a potential total contribution of several metres of sea level rise in the long term. To better quantify these risks, an international consortium of scientific teams has made Thwaites one of the most studied glaciers in the world. Since 2018, airborne radars, ice-based sensors, GPS stations, underwater robots, and deep water drilling have been deployed to access the water flowing beneath its ice shelf. Some missions have drilled more than a kilometre through the ice to the underlying ocean, collecting data on temperature, salinity, and currents. In other cases, attempts to install permanent instruments have failed due to technical issues, highlighting the difficulty of operating in one of the most extreme environments on the planet. But each measurement refines the models and reduces uncertainty about the glacier's future. Meanwhile, other studies are looking at the Antarctic ice sheet as a whole. Between 1992 and 2020, Antarctica already contributed several millimetres to the global rise in sea level, with a notable acceleration in areas such as the Amundsen Sea. In very recent years, even short periods have been detected in which the total ice mass appeared to increase, due to greater snowfall in some basins. Far from being definitively good news, these episodes show the complexity of the system. Against a background of warming and mass loss, there can be regional or temporal oscillations that temporarily mask the overall direction of change. Beyond specific figures, what emerges is a picture of great uncertainty and long-term commitment. The Antarctic ice sheet's response to current warming will not end this century. Even if emissions were drastically reduced, the system of glaciers and ice shelves would continue to readjust for centuries or millennia, with a debt in the form of rising sea levels already underway. Tipping points such as the loss of key ice shelves or the irreversible influx of warm water into certain basins could determine the fate of large parts of the continent long before maximum effective melting is reached. The Denman and Thwaites ice chasms are, in essence, windows into the future. Their behavior is shaped by deep geology, composed of buried canyons and sloping beds below sea level, ice dynamics including mass flow, fracturing and shifting ground lines, and climate change with its warming oceans, changing winds and altered precipitation patterns. The hidden Antarctic thus becomes a central piece of the global climate. What happens beneath those kilometers of ice will largely determine what the planet's coastlines will look like in the centuries to come. And yet, even in these scenarios, the continent is not just a chessboard of physical processes. On the cracking and shifting ice, and under skies that change with the climate, communities of organisms persist that have learned to live on the edge. Penguins, seals, whales and microorganisms that thrive in extreme darkness and cold. In them, Antarctica reveals another side of its secret, that of life that resists, literally supported on a moving ground. On a map, Antarctica appears as a desert of rock and ice where nothing could possibly thrive. However, upon closer inspection, the picture changes completely. Surrounding the white continent unfolds one of the most efficient met and specialized ecosystems on the planet, built upon a short food chain highly dependent on two factors: sea ice and seasonal sunlight. Unlike other oceans, here a few keystone species support giant predators, from penguins and seals to whales weighing tens of tons. The ultimate symbol of this extreme adaptation is the emperor penguin. It is the only bird that has taken its breeding season to the heart of the Antarctic winter, when darkness is almost total and temperatures can plummet below -40 degrees Celsius on the coast and much lower inland. Instead of building nests, pairs gather on the sea ice, tens or even hundreds of kilometers from the open sea. The female lays a single egg and, once her reserves are depleted, carefully transfers it to the male, who balances it on his feet and protects it with a fold of skin and feathers. For about 10 weeks, the male remains in the colony without eating, huddled in dense groups with other males, slowly rotating to distribute the wind's impact. His body, covered by a very dense layer of feathers and fat, keeps the egg tens of degrees warmer than the surrounding air. Meanwhile, the female returns to the ocean, where she must regain the lost weight and store enough energy to feed the chick upon her return. The success of the entire cycle depends on a delicate balance between the extent of sea ice, the stability of the ice floor where the colony settles, and the distance to feeding grounds. Abrupt changes in ice formation or breakup can leave colonies without a stable platform or lengthen foraging routes too much, with direct consequences for the survival of eggs and chicks. The emperor penguin is not alone. In summer, when the light returns and the sea ice breaks up, other penguin species take center stage in many regions of the continent. Adelie, chinstrap, and Gentoo penguins form large colonies on rocky coasts, where they build stone nests and feed their chicks fish and krill. Adelie and chinstrap penguins are strongly tied to sea ice, while Gentoo penguins are more flexible, taking advantage of more open waters. This difference has become crucial as some areas of the Antarctic peninsula warm up. While Adelie and chinstrap populations have declined in certain areas, Gentoo penguins have expanded southward following warmer waters. Around these colonies, the sea ice becomes a veritable transient landscape. Several seal species rest and reproduce on it. The Weddell seal, for example, lives much of the year associated with areas of fixed ice. To breathe in an environment where the surface is completely sealed, it keeps its own breathing holes open in the ice by scraping it with its teeth, allowing it to dive beneath the ice and always emerge at the same spots. This strategy allows it to occupy more southerly latitudes than any other marine mammal. At the other end of the behavioral spectrum are leopard seals, solitary predators that patrol the edges of the ice in search of penguins and other prey. With a streamlined body and powerful teeth, they combine speed and maneuverability in icy waters, ambushing penguins as they dive or return from the sea. Alongside them are crab-eater seals and other species that, despite their name, feed largely on krill, filtering it through special structures in their teeth. Above this backdrop, the sky is the domain of seabirds that travel enormous distances between their breeding and feeding grounds. Albatrosses, giant petrels, skuas, and other species use the Antarctic winds like highways, gliding for hours without flapping their wings as they search for scraps of food, fish, and krill. Some species nest on subantarctic islands and only approach the ice edges seasonally. Others have permanent colonies in less extreme regions of the Antarctic peninsula. Beneath the surface of the Southern Ocean, however, lies most of the biomass. The cold, nutrient-rich waters support phytoplankton blooms during spring and summer, especially around sea ice where microalgae grow attached to the underside of the ice. These algae form the basis of the diet of one of the key organisms in the system, Antarctic krill. This tiny crustacean, just a few centimeters long, forms swarms so dense they can be detected by sonar and even satellite. Penguins, seals, whales, fish, and many seabirds depend directly on their abundance. Krill, in turn, depend on sea ice, especially during their juvenile stages. The larvae use the porous structure at the base of the ice as shelter and a food source in winter. When the extent or duration of the ice changes, the survival of these early life stages is also affected. Studies in recent decades have detected significant declines in krill populations in some regions linked to reductions in sea ice, which translates into changes in the distribution and reproductive success of penguins and other predators. In the depths beyond where the light penetrates, the ecosystem transforms. Fish adapted to the extreme cold move slowly, some with antifreeze proteins in their blood that prevent them from forming ice crystals at sub-zero temperatures. Invertebrates such as giant sponges, starfish, sea urchins and crustaceans inhabit seabeds that, in some areas, have remained covered by ice for thousands of years. In specific locations, volcanic activity under the ocean creates low-temperature hydrothermal vents that host specialized communities of microbes, adapted to live in the absence of light and with chemical energy sources. Life also exists within the ice itself. Microorganisms, algae, and small invertebrates colonize the snow and surface ice, sometimes tinting the surface with greenish or reddish hues. In cracks and channels within the sea ice, salt-tolerant microbial communities thrive in conditions of partial darkness and sub-zero temperatures. In subglacial lakes, such as those described in the previous chapter, there is evidence of bacteria and archaea that have persisted in isolation for long periods, feeding on chemical compounds released by the rock and water. Each of these habitats represents a natural experiment on how life can organize itself under extreme conditions, with direct implications for astrobiology. This natural network is not isolated from global changes. The Southern Ocean is warming and acidifying, and the extent of sea ice around Antarctica has shown recent variations outside of historical patterns. In some areas, winter ice maximums have declined sharply, and in others, ice breakup occurs earlier in the season. These changes are reflected in the behavior of the species: modifications in the breeding schedules of penguins, displacement of colonies, changes in foraging routes of whales and seals, and alterations in the composition of plankton. Added to this is increasing, albeit indirect, human-caused pressure. krill fishing regulated by international agreements has intensified in areas near high biodiversity zones, especially around the Antarctic Peninsula. Although total catches remain a fraction of the estimated biomass, the combination of exploitation and climate change raises questions about the system's resilience. Microplastics and persistent organic pollutants carried by atmospheric and oceanic currents have been detected even in organisms that have never left these remote waters. Thus, Antarctic life is not only a story of extreme adaptation but also of vulnerability. Every penguin that travels kilometers across the ice, every seal that keeps its blowhole open, every whale that migrates following the krill's tracks, depends on a set of physical conditions that the global climate is beginning to alter. Antarctica, which for decades seemed like an untouchable sanctuary thanks to its isolation and the framework of the Antarctic Treaty, is revealed as a finely balanced system, sensitive to changes that originate far from its shores. Understanding and protecting these ecosystems requires more than admiration for their charismatic wildlife. It demands cutting-edge science, robust international agreements, and decisions about how much and in what ways humans should continue to visit and use the continent. The next step in this journey leads precisely to that terrain. Antarctica as a global laboratory, an extreme tourism destination, and the stage for an ongoing debate about how far we are willing to go to preserve the continent hidden beneath the ice.